Thank you all for coming back here, or at least most of you coming back here for our second speaker of today. It's my pleasure to introduce next Roberta Sinatra, who is an associate professor at ITU Copenhagen and the coordinator of the Networks, Data and Society Research Group, which is very appropriately abbreviated as NERDS. He's also a visiting researcher at the ISI Foundation in Turin, Italy, and the Complexity Science Hub in Vienna, Austria. She's mostly working in fields like, well, a variety of fields covering network science, data science, computational social science, and in this case, also stuff related to the science of science is perhaps the best label for the field that she's active in. She's published a number of well-known studies in this field, among which, for instance, quantification of evolution of individual scientific impact, also related more broadly to hot streaks, not only in scientific careers, but also in arts, for instance, and artists in cultural careers. Other things relates to more effects of publishing and also effects on citations related to, for instance, chaperone effect of publishing in certain journals because you're chaperoned into publishing into these particular type of journals. And more recently, working also on gender differences, being involved in a large-scale study in terms of gender differences, part of which was already raised yesterday by Hannah. Studying how gender differences in citations and productivity work on a variety of disciplines, countries, times. And today is also working on, which I understood, modeling also bias mechanisms and trying to use them to improve fairness. And I learned that you also got a grant from the Denmark Free Research Foundation in order to do this type of work. Which aligns well with what we're going to talk about today, namely the quantification of biases of scientific impact. So without further ado, go ahead, Roberta.
Okay, thank you, Vincent, for the introduction. And I'm really sorry that I couldn't join you in person. This was unexpected, but thank you for accommodating the talk remotely. Yeah, I'm missing out on a lot of what's going on there, but hopefully, yeah, at least there is the opportunity to discuss a bit online. All right, and yes, so I'm going to talk a bit about biases and scientific impact and what is really occupying my mind lately, and how we are approaching the problem of bias in science, bias in data, and the effect of these biases in measures and algorithms. And yeah, okay, here, like this. So in social system, there is a widely known phenomenon called the Matthew Effect. Of course, I don't need to explain the Matthew Effect to this audience, but let's just warm up with recapping what it is and how we can express it in models. So the Matthew Effect says that the rich get richer, and it has many names depending on the field. So for example, in network science, people talk about preferential attachment. In mathematics, mathematicians tend to talk about Poya-Earn, or also it pops up in when we talk about multiplicative processes. So depending on the field, the same effect has different names, but what is important is that it has, it's a phenomenon that drives the evolution of popularity and impact, and it has a very clear mathematical formulation. So, for example, if we talk about citations and how papers acquire citations, then the Matthew effect says that the probability for a paper acquiring a new citation depends on how many citations you already have. So, and this probability is right now on the screen. It can be modulated slightly in different ways. One can add a constant, one can add an exponent, but the fundamental point is that the probability of acquiring more impact of acquiring, for example, a citation depends on the existing number of citations. There is another effect that is present in many social systems. It is called Matilda Effect, and it says that there is a bias against acknowledging the performance of women. And this is also an effect that drives popularity and impact. But differently, despite being documented, this effect has surprisingly no mathematical formulation, no clear mathematical formulation. It's not incorporated, for example, in models of evolutions of citations over time. And the Matilda effect says that there is a bias against acknowledging the performance of women. We can talk a bit more generally about the X effect, where there is a bias against acknowledging the performance of X, where X could be race, it could be affiliation, or different attributes that a scientist can have. So what I'm going to talk about is mostly focused on gender effects, but keeping in mind that bias exists towards different segments of the population, and most of what I'm talking about in terms of methods and framework, it can be extended to study other other effects, so the X effect. So why is this important? Why did I start with about Matthew effect and the Matilda effect? Well, these effects indicate that social measures like citations or retweets if we are on Twitter, or video views if we are studying a video platform, evolve in a biased and strongly unequal way. The Matilda effect or X effect can generate a difference at the beginning of how a paper acquires citations or how a tweet is retweeted, and then the Matthew effect amplifies those differences. At the same time, we increasingly use algorithms that are trained on social measures, and we treat these algorithms treat these measures as a proxy of quality, as a proxy of performance. So proposing, for example, new content to explore. And therefore, then these algorithms become inherently biased too, and can even amplify inequalities. And let me give you a practical example of how this can happen. So the core of paper ranking algorithms is a black box, so we don't really know exactly how it works, but we know that these black boxes take paper information like title, the affiliation of authors, and crucially, the number of citations that the papers have acquired. And then these algorithms typically rank papers with many citations higher than less cited papers. And this sounds legitimate, right? Usually we want to have, statistically speaking, papers with more impact, more visible, more on top in a ranking than less, than a paper with less impact. But yet these algorithms are biased. So there is experimental scientific evidence that given same quality, given the same paper, women tend to receive less recognition. So in this system, papers by men are systematically ranked higher, providing more visibility. And again, here the example is between men and women, but we can extend it to different segments of a population, right? So papers from a person with some affiliation, more on top of the ranking, gets more visibility than people from without another affiliation. So, but at the end of the day, there is a citation bias that can affect the ranking, can affect the visibility, can even affect the recognition that we give to these scientists, because our system increasingly base the scientific recognition system, even the tenure, on indicators, rankings, and so on. So what is the overarching, also the dream that I'm trying to pursuing lately with my work is, well, first to understand and model quantitatively the bias mechanism. So in a way, open the black box, understand why some items are ranked higher than others, possibly understand if there is a bias effect there, and then using this knowledge, using this understanding of the bias mechanisms to unbias rankings, or to improve to lower to improve the fairness, to lower the bias in the rankings or in measures, and provide a more equally distributed visibility based on some, of course, on some assumptions. So I've been working on science, on the science of science, yeah, for a while now, for around 10 years, and to discuss how we have been thinking about bias and how we can capture that in the data. I had to shortly step back to 2016, when we were thinking, we were addressing this question. We wanted to know how does impact in scientific career evolve. So effectively, what we were doing, what we wanted to do, was creating models that would capture the evolution of impact as captured by citations, the evolution of impact over time of scientists. So basically reproducing the ups and downs of the impact that a scientist has when publishing papers. And when I'm talking about careers, I have in mind something like this. So a very rough or brutal approximation of a career. This is the career of Richard Feynman. Basically here, each red dot on the screen is a paper of Richard Feynman. On the x-axis, you'll see time. And the height of the dot captures the impact that paper had, and is quantified with number of citations accumulated over 10 years after the publication of the paper. So our goal back in 2016 was, well, to understand when a scientist will make their highest impact paper. And so when, this is the time, we call this time the T star, so the time of the star paper, and the magnitude of that, of the magnitude of the impact of the highest impact paper. So to do this, to predict these two numbers, effectively what one needs to do is to have a model that captures the stochasticity of a career, represented by this time series, so to produce the ups and downs of this career. And we did so, we proposed a model that works well, captures the ups and downs of impact, the evolution of impact of 85% of the scientists, and it does so in for sure in a mathematically beautiful way by associating one number, which we called Q, to each career. So each scientist, each time series has a Q value. And given the Q value, we can predict basically the impact over time. So I will not go into the details of this paper. The paper is published, and there is also a video on YouTube, a 5 minutes video summarizing the major findings. And also we have a platform where you can explore the data that the paper is based on. But starting from that work, I started having the obsession of, okay, so we have a number Q that can summarize the evolution of impact of a career. And this number, this Q, or this model had quite a bit of resonance because so many funders or in many editors were starting asking, well, can we use Q as a synonym of quality? Is Q a better way of identifying scientists that will do like major discoveries or that produce better, let me use the word better with quotes, than other scientists. So the equation Q better quality was floating around a lot. It was not when we thought about the Q model to summarize careers. We were really interested more in a model that could capture the stochasticity of those careers. So I started really reflecting on this question: how do performance and impact in science differ? Or in other words, how can we interpret Q? What is it really? And here is where the discussion of biases intervenes, right? So as I said, I will focus on gender bias and the effect of gender on impact. But I've been working also on other impacts that occur in the data that we use. So, for example, the disability bias or the reputation bias. But there are many more, right? And this is why I think the problem of bias is really, and possibly a bias in data, it's more, should be more a community research agenda rather than just a group or a few groups agenda, because there are many biases to tackle and to uncover out there. But so going to gender bias and the Q model, so what we did shortly after publishing the Q model was to, for example, see how Q is distributed in different segments of the population. For example, the population of women scientists and the population of men scientists. And if we study the different distributions, we see that, for example, male scientists have on average 50% higher Q than female. Does this mean that on average male scientists do better, higher quality work than a female scientist? Well, my gut feeling should say no. Then one needs to understand why. Where does this difference come from in the data? So effectively, what the Q model does, it manages to reproduce the ups and downs of a career. So manages to if you want, separate the noise, we call it usually luck, the noise in a career. But it does it in the same way for all the scientists. And indeed, we can show that there is a random component, which we call luck in a career, that is the same for all the scientists, no matter the gender or the affiliation. So to understand whether there is really a difference in quality in work between two different segments of the population, and if this is reflected in the citations acquired by paper, we will need to have randomized controlled experiments, or one way, good way to tackle this problem is with randomized controlled experiments. These experiments do not really exist to see if the same paper with different attributes would acquire different citations, because it's basically impossible to do there in the wild. But there are papers that show that so there are, sorry, not papers, there are experiments that show that actually given same quality or given the same performance, for example, women tend to receive different recognition. One of my favorite experiments is one that was done by Rakusin, and the findings were published in PNAS in 2012. What they did, they had scientific committees that had to hire a research assistant, and they were giving to these committees CVs of applicants, and different committees were assigned to a treatment and control group, and the treatment was changing the gender on a paper. So two committees were receiving the same identical, sorry, I said paper, changing the gender on a CV, on a CV. And two different committees were getting the exact same CV with just the name and the stated gender changed. So Jennifer, female, would become John, male. All the rest was equal. And the results were definitely shocking. So given the same CVs, female applicants were considered less competent, less hireable. They would have been offered less mentoring opportunities than male applicants, and female applicants were offered also a smaller salary than male applicants. So then I said that this is one of my favorite papers. It has some shortcomings, like the size of the group was not big. Changing the context, changing the field, and changing some of the experimental conditions. Other people found different results. So I think that all of this needs to be explored better. But nevertheless, what I think it's important here is that provides a framework, a design that, given same performance, shows different impact or different potential evolution of the career of a scientist. So a bias can be definitely out there and can have an effect on the evolution of a career, especially at early stages. So we wanted to tackle this question of what is the role of gender in career differences in the data in observational studies, but trying to mimic as much as possible the setting of a randomized controlled experiment. And so we were asking, how does productivity differ between female and male scientists? How does impact differ between female and male scientists? And we'll tackle this question first, straight away on the data, and then we'll mind something like a randomized controlled experiment. So the first thing that one needs to do is taking a career, and one can assign a gender based on the first name of the author. Here we are using a binary gender. Of course, this is an approximation, so we are not able to capture all the nuances of gender identity. But this is what the data allows us to do, and in a way, this is also what a reader usually does. So sees a first name, which is either female or male, one can be identified, and possibly some stereotypes or bias kicks in then. And when we divide careers in female and male careers, and we do measurements of number of papers, impact, divided in different countries. So we do all the possible measurements that we can think of. We see differences everywhere. There is, gender difference in almost all the measurements. So I want to just flesh out some important differences among the quantities that we measured. So in the data that we use, male scientists constitute 70% of the scientific workforce. They get 30% more citations. They are more productive, they have more papers, and this productivity gap is increasing. It was 10% more, male scientists had 10% more papers than women in 1950. And in 2000 was 35% more. So the gap is increasing. Surprisingly, if we look at annual productivity, so how many papers are published on average per year, we don't see differences between female and male scientists. And we can reconcile the fact that there is more career productivity for men and same annual productivity for women and men. We can reconcile this by observing that female scientists tend to have shorter career lengths. So they have basically, although the annual productivity is the same, they have less time to publish papers, and hence less productivity over the whole career. And indeed, so women have shorter career lengths because they exit academia at a faster rate than men. This is not surprising, no news, we know that. What I think was interesting in this work that we did is that this dropout rate is very different over time. It's very different during a career of a scientist. And it's not that different between men and women during their PhD. So the dropout rate is more or less the same. It's the difference is the biggest around 7 years after a career starts, which is the time during a postdoc or an early tenure, usually. So this is when the biggest dropout occurs, and then the gap in dropout stays there through the whole career, meaning that even 30 years after the start of a career, women tend to drop out at a faster rate than men. So the reason why we find differences everywhere in all the measures that we make is because there are confounding factors, and we want to understand a bit better if you want, what are the causal directions. So does, for example, dropout induce more differences in productivity, or does productivity induces differences of impact, and so on? And to do this with data, so when we have large data sets, as we did, the closest that we can get to a randomized controlled experiment is to use a matched sample approach. So we were using 3 different data sets that had between hundreds of thousands or millions of scientific careers. And because of the large volume of these data sets, we could do a matched sample approach where we basically were matching on features, matching on controls. So for each female author that was, for example, an American physicist with a career of 10 years working at an institute ranked a certain way, we could find a male author that that is also a physicist, that has also a career of the same length, and also works at an institute ranked in a similar way. And we can then construct matched samples for female, so 2 matched samples, one of female authors and one of male authors. Of course, this approach has the limitations that cannot match on unobservable variables. This is the biggest problem working just with data, with not coming from controlled randomized experiments. But still, we can see what happens here, and we can reflect on the differences that we observe, and for example, what happens when this data is then fed to algorithm, because the algorithm also has access just to data, not to the results, for example, randomized controlled experiments. So when we look at productivity in the population without, so straight away, without doing the matched sample approach, we see that there is a difference of productivity, which is 27% in the whole population for all the years. This is something we have seen already. If we do the same measurement on the matched sample, so where we control for career length, where we control for disciplines, country of affiliation, and so on, then the productivity gap shrinks. It becomes 7.8%. And if we measure total impact on the whole population without controls, the impact differs by 30%. If instead we create a matched sample approach, as I said, plus we control also for productivity, so we take 2 populations that have the same distribution of number of papers, then the difference in impact basically disappears. It's 0.8, but it's not even statistically significant between the 2 samples. So this means that how does productivity differ between female and male scientists? Well, it's only by 8% if we take into account the discipline and dropout rate. And how does impact differ between female and male scientists? Well, there is almost no difference if we take into account of confounding factors. Now, if so, this is just by doing an observational study, but we know that algorithms, for example, ranking algorithms, typically do not construct matched sample. They are oblivious of the causal links, possible causal links between variables. So our question was, how do gender disparities affect ranking and algorithms? So if we think that quality is not correlated, for example, with dropout rate, or not in different ways between the male and the female population, so the difference is not due to differences in quality, but for example, in stereotypes or different working conditions and so on, then that difference is not quality is present also in the data, is present also in algorithms, and algorithms might be create a difference not based on quality of work, but on other factors. So how do gender disparities affect ranking algorithm? Based on these observational studies that we did, we know that we're pretty confident that algorithms capture, so embed some of these biases. And we studied the citation network between scientists, because many of the platforms use ranking, network ranking based on this data to provide, for example, a ranking of authors or ranking of papers. And specifically, we studied PageRank based on the network of citations. And there are 2 questions. How fair are the rankings based on citation networks? And can we increase the fairness of these rankings? And so what does it mean that a ranking is fair? So there can be many definitions of fairness in ranking. I will use one which is very common, at least in the field of algorithmic fairness. and it's called Demographic Parody. And basically it studies the top parts of the ranking, or a portion of the ranking, say top 1%, top 2%, top 10%, and so on, and see whether this portion of the ranking, in this portion of the ranking, there is the same distribution of the population as in the whole ranking. So, for example, if we know that we are studying a population of females and males, 50% to 50%, say, but this can be easily extended when you have different distributions, like 80% and 20%, then we look at the first n positions. So for example, here we have n equal 8, so 8 positions, and we'll look whether we find 50% of 50% males or females, or if we don't, what is the difference from the demographic distribution. So in the ranking on the left, we see that there is statistical parity or demographic parity at the 6th position. So if we scroll up to the 6th position, we will find 50% males and 50% females. Before the 6th position, there is no demographic parity. While in the ranking on the right, demographic parity is achieved only at the 8th position. So we say that the ranking on the left is a fairer ranking when we look at the first 8 position than the one on the right. Of course, things can flip if we study the whole ranking. So, so we did this when, so we studied the ranking based on the citation networks and looked at which portion of the ranking we need to observe to achieve demographic parity. So we go with the first 1%, first 2%, and so forth and so on. In economics, so when we study the citation network within economics, we achieve demographic parity only when we reach 81% of the ranking. So it means that we need to arrive at the 159,000th position in a network which has roughly 200,000 nodes to find the same amount of women and men in that portion of the ranking. And economics is one of the ranking, is one of the networks where there is, where demographic parity is achieved, let's say the latest, so is achieved at when only at the 81% position. The other fields have achieved fairness as captured by demographic parity earlier. Psychology is the best one, achieves statistical parity at 63%, which is still bad news. So this is when it's done straight away on the whole citation network. So the question is, can we improve the ranking? Can we make it fairer, where fairness again is captured by demographic parity, having the same representation of men and women in the ranking? And it can be done so by using again a matched approach, a matched sample approach, matching career and affiliation. So if we do the same thing as we did before, where what we want to enforce is similar distributions of the variables that are not impacted, that are not productivity, then we see that the ranking on this matched sample is fairer, so it achieves demographic parity earlier than the unmatched sample. So we go from 81% to 36% in the case of economics, or in the case of psychology, we go to 63% to 10%. So how fair are the rankings based on citations? They can be extremely unfair based on the notion of demographic parity. Of course, we need to believe that demographic parity captures fairness. We need to believe that what we want to do, what we want to achieve is demographic parity. And I think with the observational study that we showed before, demographic parity is something that we should wish for. And can we increase the fairness of these rankings? So can we have a technical solution? Well, there is a technical solution. For example, we can use matching, affiliation, and career variables. So why should we care about correcting biases? Correcting them this way or in another way, but why do I think we should tackle this problem? Well, I think we should tackle this problem because at the end of the day, when we go on whatever platform engine that we have out there, it can be Google Scholar, Microsoft Academic, Web of Science, or the future one, what we want to find is the most relevant paper, is the paper that contains the most important information, right? So I don't know if we look about papers on a topic of climate change, we want to find, what is most relevant and not what the algorithm thinks is most relevant based on data that we know is strongly biased, and biased because of factors that have nothing to do with relevance or quality, right? So all the experiments and analysis and evidence that we are accumulating show that citation data can do not capture simply quality, but they are entangled with they're tangled with much more than simple this is a sound piece of research. And so this is also something that we so this is one reason we want to find the most relevant research out there. We want algorithms to select it in a non-biased way, while we have a lot of evidence that they contain bias. And also, we want to be sure that if an algorithm or whatever model does some prediction based on the data that we currently use, so publication data, grant data, citation data, and so on, this prediction, again, is not biased. And we know that there are many services lately that propose, for example, they claim to help editors or journals to triage paper, to desk reject paper, or to send papers to review based on the projected impact of that manuscript. So there are services, there are actually press releases out there that you can check and say that they can predict the impact of a manuscript, and if the manuscript is below, the predicted impact is below a certain threshold, they suggest an editor to desk reject that paper. But this is terrible news, because if the projected impact is biased, then we are reinforcing inequalities, right? Papers by certain segments of population, they don't even reach the peer review process. So I think crazy stuff out there, and we really need to combine what we know in the science of science, what we know in the philosophy of science, and so on, with what is being done in the algorithmic sector and the production of new technologies. As I said, gender is only one of the biases out there. There are many more. It's relatively, it's easier to study gender bias than other biases, even because of technical reasons. For gender, we can use a binary approximation, and also making matched sample approaches is easier, and so on. But there is much more to be studied. But at the end of the day, if we want to answer the question, do performance and impacts in science differ? Do performance and impact in science differ? They do. They do a lot. And personally, I think that we really need to, as a community, understand why do performance and impact in science differ. So really work a lot on the causality and use it for measures, use it for how the scientific enterprise works. And how this difference affects our lives is I think it's also an important thing to tackle. And it's actually the topic of 2 grants that that I got recently, and yeah, we are currently working on these 2 questions. It takes a village to do this work. It took a village to do this work, and I have many wonderful collaborators that work with me on on papers that I presented, but also on the whole line of Science of Science. I will not mention them all individually, but they are for sure they were important the whole process. And yeah, and also I have great institutions that support me, great funders, and I thank you for your attention.
Roberta, it was a great overview and some well, very relevant questions, obviously. So not only 1 grant that I mentioned, but even 2 grants for studying this topic. Great to see that. Are there any questions here from the audience in the room, or perhaps questions from our online audience?
This was really interesting. Thank you. In the spirit of starting with clarifying questions, I was interested in how exactly the matched pairing fed into the algorithm to make it. Oh, sorry, I should. Oh, am I even on the camera?
Can you hear Hannah?
She looks like she can't hear.
I can hear some of it. So if there is a way to speak into mic, directly into the mic, it would be helpful. Yeah.
Can you hear me better now?
Yeah, let's try in case I answer a different question. Yeah.
Well, so the first thing I said was that this was very interesting, and thank you. So I wanted to ask a clarifying question about how the matched pairing fed into the algorithm in order to make it fairer. So how exactly does that affect the page ranking?
The what goes into the ranking? I missed that word. The most crucial one.
The match sample approach.
The match. Yes. How does it go into the ranking? Is that?
Yes.
How does it affect the ranking? Yes. So we basically do the ranking in the whole data and the ranking just in that portion of the data, right?
How does that feed into,
yeah.
So if I was doing like a Google Scholar search, how does that feed into which paper I would see first?
So the Google Scholar search contains much more information than just the ranking of the paper, but suppose it, so, and also we cannot know for sure, right? There is no documentation of Google Scholar, but the idea is that Google Scholar has a number of variables associated with with each paper, and the one of the variables is either ranking straight away, page rank, or normalized ranking, which is effectively like something like a percentage, where you are in the percentage of the ranking. And then that is fed, that produces a bigger ranking, also using other information. So the page rank is not the only variable that is taken into account, but it's one of the attributes associated with a paper together with others, and then that produces what we see online. So I know that I'm not tackling directly the problem of how Google Scholar is directly biased. So the problem is downgraded to studying how bias affects page rank in a network, but we do know that that has an effect eventually on the platforms. How? It's something that I wish we could study. We haven't done it there in the wild. So I think teaming up with people that can actually harvest or reverse engineer the ranking on Google Scholar, so to understand how it works would be great, but we haven't done that yet.
Thank you.
Oh, we don't, yeah.
Yeah, thank you very much. Linked to this, so I'm trying to understand how this would affect ranking of articles if we believe that affiliation and career stage or career length predict the quality or relevance of an article. So as I understand it, this matching would take these predictors to some extent out of the equation. But if they are relevant, they would make the ranking less relevant in terms of selecting articles. Obviously, in terms of evaluating scientists, they should be accounted for. So I don't know if I understand you correctly, and if I do, then whether you think it might reduce the quality of article rankings.
So are you asking whether removing information, because we do remove information by using a match sample approach or by making the distribution is equal, then reduces the information at the end in the ranking? Is this?
Yeah, whether if these two pieces of information are correlated with article quality, whether
yes,
it's reducing the quality of the article ranking.
Yes, then yes, if we believe so, yes, it reduces it would reduce the quality of the items that we see in the ranking. So it's really a matter of agreeing on assumptions. I think that the controlled experiments that we have out there show that productivity and impact, they evolve in an equal way that do not have much to do with quality. So, for example, these controlled experiments, randomized controlled experiments about evolution of the career of research assistants would show that. But I think as of now, to my knowledge, we don't have really like investigations at such a high longitudinal way to say that productivity and impact really correlates with quality. So this is why I think, and I said it while I was presenting, that we need to agree on the assumptions. We need to agree on what is fair. I do think that there is no reason why two segments of the populations, like male and female, produce work of different, really of different quality, or we should be very careful about the technology making this assumption for us, because it's doing that, right? If the technology doesn't make this assumption, so for example, we give visibility to both segments of the population, and in the end there is a difference in quality because our assumption was wrong, then that will self-correct anyway, right? Not because the technology provides the same visibility. I think here, yeah, it boils down to agreeing on assumptions, and this is also one of the big questions in the whole field of fairness in algorithms and platforms and so on.
Yeah,
Very briefly. So, I mean, if we don't believe that career length in institutions are predictive of research quality, I mean, then something is wrong. All senior scientists who have more resources should be able to produce better quality. Otherwise, I mean, the whole concept of research funding doesn't make much sense. That it is unfair that is correlated with gender, I completely agree. I mean, obviously, that shouldn't be correlated with gender. But if it is, I see a challenge correcting for that in evaluating the relevance of research.
Yeah. So wait a second. When I say that we match for career length, we match for productivity and so on, we still have a distribution, right, of productivity, of career length and so on in the data. So means that so make it in a very simplistic way. Women and men, they have the same visibility in the ranking in this matched sample approach. But people with different productivity do not have the same visibility. So for example, a person, regardless of the gender, with more papers might be placed more on top than someone with less papers, right? So the fairness applies only to the gender difference, but not to the career, productivity, and so on differences. So if quality is correlated with career length, still there will be it will be reflected in the ranking. Does it make sense?
Yes, I believe.
Yeah.
Thanks, for that. Next question.
And I can just look into my computer here. For once, I've got a quick question. You mentioned in the match sample experiment that there were, because of the data set, you had unobservable things that you couldn't include. Could you just articulate for us what you think the most important of those unobservable things were that you would like to control for if you had a perfect data set?
This is a difficult question because I haven't, let's say, ranked the unobserved variables, right? We know that they are out there, but I don't know, for example, attempts of publishing, right? That could be very important. So it could be that a person would have many more papers if we could take into account also the unpublished stuff or the rejected stuff or stuff that stays in the pipeline longer, or things that are more even more elusive, right? So like there have been recently papers talking about the bias of mentor choice. So there are students with students tend to prefer male mentors toward instead of female mentors, and then there might be differences in the population of students that join the group of the research group of a woman in respect to the group of a man. But I'd be honest, I haven't really thought what is the most unobserved variable out there. Yeah, it's something that, yeah, I really I haven't sorted in my mind. Honestly, I think, yeah, there are so many things that we should or we could measure or we should collect data about beyond the publication data sets or the academic data sets on a large scale, that I think any bit of more information is welcome. Any more bit.
Thanks.
Yeah.
Yes, I have a very basic question. Perhaps it's just my stupidity that I don't understand. But I've never been able to understand why the sheer number of citations is seen as indicative of the quality or relevance of a paper. Since when you cite other peers, then that may be for very different reasons. You may cite them because you're critical of them, but then you can say, okay, at least they are worthy of criticism. But you can also cite papers because you want to have an example of a clear view or a pure view, and even that's often that's an extreme view, right? So it means that if you just count citations, that you get what you see in society as well. The more extreme voices are more likely to be included than more nuanced voices. It may be qualitatively better.
Yeah, I agree with you, but unfortunately, this is not what happens in practice, right? When we see whatever quantifications of impact in the future, I rarely have seen measures that capture these nuances, right? These differences and nuances that you mentioned. So I don't know. As I said, platform, but even just a regression that wants to predict the impact of a paper with the goal of desk reject some manuscript in respect to others. So those models, those regressions just use number of citations as it is, perhaps normalized by field, perhaps with some small normalizations, but definitely do not take into account all these nuances. So just to be sure, I don't believe that citations corresponds to quality, right? It's this is actually the narrative that I would like to help dismantle, or to help correcting, or to help understanding. But in practice, in many situations, this is what it is. For those, for example, familiar with the Italian system of hiring researchers, professors, and so on, there are a lot of indicators based on citations that are being used there, and they are based on the raw number of citations, assuming more citations, better. And that affects decisions, right? And this is something that deeply bothers me. Yeah, but there is also excellent work out there saying that yes, so citations, there are many kinds of citations, and we could automatize, or we could take these different kinds of citations. We could then take them into account in measures, in metrics, so forth and so on. But I have not seen it used for practical purposes. And please, if somebody thinks differently or knows of attempts that do it, let me know. Yeah, I would love to hear. Yeah.
Thanks for the talk. I would like to follow up on exactly this. So the measures that we now use started basically in the library, so that they wanted to know, what books to buy and then papers and which not. The idea is that if science is done right, then a high quality paper receives citations and a shit paper, excuse my language, does not. But this now becomes inverted. My sense is that the computational work that you're doing relies on these measures, and then also sort of in the interpretation of the results also has this inversion in there. So you want to measure quality, but you can't. That you have is not a measure of quality, it's a measure of citation. So how confident do you feel about what your results are in view of this problem?
So
you cannot measure what you're looking for, it's sometimes say. Not with the tools that you have.
You cannot, we cannot measure quality, I know. So what do? We still need to sort information, right? We still, even because the amount of papers, amount of information we are producing is growing every day. So we need technology to do the help, to help us, right? So we have this problem. We cannot measure quality directly, but we still need the technology to help us. So how do we do? As of now, we are using all the information available, so all information about papers, plus how the paper is cited, right? And that helps in sorting information, because there might be some truth in the end, that citations capture something between like very important discoveries and shitty ones. Sorry, I used the same language, or let's say less important ones. But between not using citations and using them as it is, I think there is a whole spectrum of possibilities. And what I'm claiming is that computationally, we can adjust our knobs so that we do not measure quality directly, but that we reduce the effects of biases that we know are out there. Dropping the information altogether is something that I think we can't do, because we will, as I said, we need the technology, we need to sort papers, but using this information as it is problematic. And it's not a yes or no question, there is a whole spectrum in between. It's true that we cannot directly measure quality, totally agree. I think that we can, even not in a perfect way, in perfect ways, but ways that can be improved over time, and this is why we do research, we can reverse engineering more and more how impact differs from quality and take that into account. I hope that my motivation makes sense. Yeah, this is what is in the back of my mind, right? That we don't need to equate citations with quality, but we don't need also to drop it altogether. There is a whole world in between.
I think first in the back. Yeah.
Yeah, going further on this point, I have 2 points. I was wondering about, for instance, you have a discussion in a certain field in a certain era, and maybe there's this dynamics that after a couple of years, the research that is fit, as you said, would be cited less and less, because first you go with a group of scholars, you go against an argument, and then you sort it out and you get a level of consensus. So I was thinking about the same thing. Maybe over the years, this effect will lessen, if you would believe in the progress of an argument. And the second thing might be a bit of, yeah, don't know if it would be practically possible, but couldn't you think about authors incorporating a different way of citation, that you would, as a writer, say this is a positive citation and this is a negative citations, which would also be a way to further in the process get a view of what the main consensus is in a certain discussion. I just thought.
Yeah. So let me just take a note, otherwise I forget. So regarding the fact that over time, you're saying that like the system could self-correct. Is this what you're saying?
I'm not sure if it does, but yeah, maybe this would be a factor in this.
I don't know. I don't know if it can self-correct in the end. My impression is that, well, it depends also on the time scales, depends on many things. But if the Matthew effect stays there, so if the reinforced mechanism is always there, and we do believe that there is a difference in perceived quality. So here I'm thinking model-wise, right? Then even on the long term, we wouldn't see a self-correction. I don't know if there are studies about this. It would be definitely interesting to do. Again, there is a problem of controlling for quality, which we can really do. But speculating at the model level, so if there are some models that we believe do a good job in capturing the evolution of citations, I would think that if there is a difference in perceived quality, that stays there over time. But it's definitely something interesting that one could reflect on or work on. And instead, regarding like you're saying, so like we should start a practice of when we refer a paper to signal whether it's a positive citations or a negative citations or a neutral one. Was this the question?
Again, I don't think we should do this. I think it's an interesting thing. Well, would think about.
It's something. Yeah, it could be. It's something that at some point we discussed to give like a sentiment or to try to assign a sentiment to a citation based on where it occurs in the text. So based on the information around the reference, but we have never followed up on this, and I don't know, it would be something cool. I'm just not aware of work work doing this. I see that someone on the chat wrote that there are some Cite AI does this. Okay, I was not aware. I will look into this, that they disambiguate citations. Yeah, cool. Thank you for this. Yes.
One of the things I want to say as well. This is one platform that does that.
Okay. I was not aware. I will look into it. Yes.
So we have perhaps time for. Oh, there it's 3 times mentioned actually at the same time. Okay. So one last question.
Thank you so much. I was a little bit frightened by what you showed, what Meta is trying to do. But I'm also intrigued. I would really like to hear your speculation as to how they do it. Because at least, I'm not an expert, it seems that you want to have some sort of measure of, things that tend to be sort of impactful, might be things that have big effects, and I understand how that can potentially be detected. But there's also very often sort of level of surprisingness. Do you think those are the sort of things they're using, or could you speculate a little bit how that works? I'm frightened, but I'm also intrigued, and maybe you can illuminate me.
Yeah. So actually, we tried to understand more about this. So there is not much more than the press release that there was. That press release is already 2 years old or something like that. So and I'm not up to date with the follow-ups of what Meta does, but all information out there was the press release, and the press release explicitly say that they want to, that the metric is maximized. So finding the papers that will have high impact, right? And the problem is this, that it's not, we don't know how they work, right? And this calls for transparency of the algorithm, sort of the methods and so on. I want to believe that it was not just citations or something based on citations, but there was not, based on information press releases, it seemed just that, right? And it frightens me. So it frightens me that such initiatives are out there and that there is no transparency. And I hope that by doing research on this area, so research like the one that I showed, or research, similar research, if companies producing these tools become aware and change their optimization metrics, right? Or aware that optimizing for a certain metric is a bad assumption, a bad idea. But we don't know much. So I'm sorry that I cannot elaborate much. I cannot say much more on what exactly is done. But for sure, there are tools out there that companies are trying to sell.
Okay, Thank you for that last answer in this case. So thank you again for the presentation.
Thank you. Thank you.